Hello and welcome to the IEA Greenhouse Gas webinar programme. Our webinar today relates to the understanding the cost of retrofitting CO2 capture to integrated oil refineries, the ReCap project. Our presenters are Rahul Anantharaman and Simon Rustenali from Sintef Energy Research in Norway. Rahul is a research scientist at Sintef, and his research interests are in systematic design of chemical and energy conversion processes, with a special focus on process design and optimization of power plants and industry integrated with CO2 capture. Simon is also a research scientist at Sintef, and he focuses on techno-economic modeling, optimization and analysis of carbon capture and storage, CCS, natural gas and hydrogen value chains, with a special interest for CO2 capture and transport. So I'm now going to hand over to Rahul to take you through his presentation, followed by Simon.
Thank you for the introduction, Susan. Good afternoon, everyone. In this presentation, my colleague Simon and I will present results from the ReCap project, where the goal was to understand the cost of retrofitting CO2 capture to refineries. To start off, a little bit about the ReCap project. The project was coordinated by us at Sintef Energy Research, ieaghg, the operating agent of ieaghg, and Concave were industry partners in the project. Concave is a division of the European Petroleum Refiners Association that carries out research on environmental issues related to the petroleum industry. ieaghg Foster-Wheeler were a subcontractor in the project. We mainly use them for their expertise as an engineering contractor in the energy sector, particularly the refining sector. And the main funding agency was the Research Council of Norway through their Climate Demo program. Now, the global refining sector contributes to approximately 4% of the total CO2 emissions. And CCS is a key technology to curb these emissions. There are no new refineries that are expected to be built in the OECD countries, so the study of feasibility of cost of retrofitting is very important here. It is also essential to have a good understanding on the direct impact on the financial performance and market impact that is imposed by retrofitting refineries with CO2 capture technology. Now, retrofitting is one of the key aspects of this study, as you would have found out by my use of this word quite a bit. So what motivated us to do this work? The policymakers should fully understand the cost of CCS deployment. Now, in a refinery, there are multiple emission sources, and the strategies for capturing such a situation have not been studied.
The broadcast is now starting. All attendees are in listen-only mode.
The current open literature also does not provide data that are comparable to one another. The studies that are done so far have also been used a top-down approach, and the problem with this approach is that the results cannot be taken out of context and are very specific, which is why what we wanted to do as part of this project is use a consistent bottom-up approach. And using a bottom-up approach is important because then it's possible to extend the results that we obtained from this study to the other refineries. And this has been an important motivator on the use of this bottom-up approach, the fact that we can extend the results. I'll talk a little bit more about that later as we go to the results part of the presentation. So as part of this study, we looked at 4 generic base case refineries. We defined these 4 refineries, which were a simple refinery with a nominal capacity of 100,000 barrels per day, medium and highly complex refineries with nominal capacity of 220,000 barrels per day, and a highly complex refinery with a nominal capacity of 350,000 barrels per day. Now, each of these base cases are we tried to make it representative of existing European refineries in the same sizes. So here, Concave and AMEC Foster Wheeler led this effort to make sure that these were representative. So as part of this project, we built detailed design of these refineries' base cases, including developing plot plans for each of them. And these were developed based on a defined set of feed and product slates, similar to what you would expect in a typical refineries of these types and sizes in Europe. And again, we started off by defining base case 1, and base case 2 was basically an evolution from base case 1. So refinery base case 2 evolved from refinery base case 1, and similarly refinery base case 3 evolved from the refinery base case 2. The very highly complex and large plant, which was base case 4, was decided to be built from scratch. So we had, as would be in a normal situation, so it wouldn't be an evolution, but we assumed that it would have been built from scratch and a greenfield project in Spain. So that is how these 4 refineries were defined. So the next few slides, we show how the CO2 emissions from these refineries. The first one is base case 1. Here you see that the largest emissions come from the power plant, which is basically a CHP plant, which is with the gas boiler with a steam turbine. And then we have the CDU, which is the crude distillation unit, emission from the furnace, and then the catalytic reforming, and then the vacuum distillation unit, and the hydrate desulfurizer. So these are the 5 largest emitters of base case 1. When you go to base case 2, which is an evolution of base case 1, we see that we add an additional train, an additional crude train in base case 2. And also we add a fluid catalytic cracker unit and a steam methane reforming unit here. So in both these cases, the power plant or the CHP plant is a gas boiler with a steam turbine. Now base case 3 subsequently evolves from base case 2. And here the main difference is that we add a delayed coking unit to the plant. And the power plant here basically is mainly a gas boiler, but we've added a very small natural gas combined cycle to it to provide additional steam and power. And lastly, base case 4, this one is developed from the ground up. So here you see that both the crude units are of the same size as compared to the other cases where they were of different sizes. Here the crude units are of the same size. We have 2 SMRs, the steam methane reformers, and the FCC is of nearly the same size of base case 3. So these are the emission levels of the base case 4 refinery. Here the power plant is natural gas combined cycle, mainly a natural gas combined cycle with a very small gas boiler added. For post-combustion capture, we consider post-combustion capture using monoethanolamine, MEA. The reason we use MEA is that it is a mature technology, and MEA is used in many ieaghg and other open reports such as EBTF as the reference solvent. So the standard configuration of the MEA process is used in this project, with the only difference being we added an intercooler in the absorber. The capture rate was fixed to 90% for the different emission sources, so for the capture plant. One big assumption we made when we started doing the design is that there were no synergies with the existing refinery. What we mean by that is there is no heat integration with the refinery, so there's no possibility to exchange steam or power with the existing refinery. there is no chance to exchange cooling water. So if this plant needs cooling water, what it is done is you need to build a new cooling water plant and things of that sort. So there is no synergy considered. So what follows is that if to supply the steam and power for this capture plant, we need to build a new CHP plant. And for each of the capture cases, we would consider a different type of CHP plant, different type and size of CHP plant I'll go through it later on as we go on. Also, one of the decisions we made is that there would be no capture from the CHP plant. So in general, the net capture rate drops down to 60% because the emissions from the CHP plant reduce the overall capture rate. So the reason we made these decisions was mainly so that the results presented here can be extended so that it is not specific for a certain case. And it's easily possible to take our results and apply it to other cases. Right. So we're starting off to look at the different cases that we consider, the different capture cases. I'll mainly present base case 4 in this presentation. That's because 4 is the most relevant for modern integrated refineries. So the 5 largest emission sources in base case 4 are the power plant, the CHP plant, and here, as I mentioned earlier, there are 2 emission sources. One is the natural gas combined cycle, which is the main source of power here. So, and also the main emission source from the power plant, which has a CO2 concentration of approximately 4.2 volume percent. And the other smaller emission source for the power plant is the gas boiler, which has a concentration of 8.1%. Totally, the power plant constitutes approximately 21% of the overall refinery emissions. The second case, the second emission source, D2, is the fluid catalytic cracking unit. Here, the emission comes from regeneration of the catalyst. The catalyst is regenerated by burning it in air, in an air environment. So the carbon deposited on these catalysts is burnt off. That's why the CO2 emissions come from here. So the CO2 concentration is approximately 16.6%, and the FCC units constitutes approximately 11.5% of the overall refinery emissions. Now, the crude units, crude and vacuum distillation units are the next emission sources, both trains A and B. They are very similar units, and the emission here comes from the furnaces of these units. So here they burn fuel oil to heat up the crude and the vacuum bottoms here. So the CO2 concentration is a bit higher here compared to gas boilers. So here it's approximately 11.3%. And the total emissions from each of these crude and vacuum units are 10.5%, constitute 10.5% of the overall refinery emissions. Finally, the last emission source we're considering for the base case 4 is the steam methane reformer. This is a large, there are 2 SMRs here, and they constitute to 25.1% of the total refinery emissions. And the CO2 concentration is 17.7%. Here it is considered that we are capturing CO2 not from the syngas, but from the flue gas exhaust, so that we have a higher rate of capture compared to this approximately 60% we would have if we capture it at the syngas level. So it is more of a post-combustion scenario. Now, each of these cases burn different fuels. So the power plant, we use natural gas. The crude, we use fuel oil, as I mentioned earlier, and so there are different emissions, or the sulfur emissions from each of these are different. So for the power plant, we wouldn't need a flue gas desulfurization before it goes to the MEA unit, whereas from the FCC and from the crude units, the emissions the sulfur emissions need to be reduced to minimize the loss of solvents by degradation in the MEA process. So we need to make sure that the sulfur levels are reduced, and so we need to put in a flue gas desulfurization unit prior to it going to the capture plant. Yeah, so the capture cases have been developed in discussion with our partners, and the main idea was to cover. We decided to cover a large range of total refinery emissions. As you can see from this table, we cover going from approximately 21% to 78.5% of the total refinery emissions at different stages. And the idea was also to study the effect of CO2 concentration, what would be the effect if we add an FGD and things like that. So we tried to put in different combinations to study these effects as part of this project. And one of the things that, again, we decided on before going to the detailed studies was that each of these emission sources would have its own absorber, and we would have a common regeneration unit. So, for example, in base case, or in the capture case 0403, as shown in the table here, each of the 5 emission sources, D1, D2, D3, D4, D5, each of them would have their own absorber, and all of them would go to a common desorber that is be located in another place. And the reason for that was that the large flue gas ducts that would need to collect the flue gas to a common absorber would be impractical and very expensive, particularly in retrofit situations, so which is why we considered having individual absorbers. So in some sense, the first table defines the absorber system, and the table 2 then defines the regeneration system. So there were 6 capture cases considered for base case 4. There were a total of 16 cases. So we had an additional 4 cases from base case 2 and 3 each in base case 3 and base case 1. So we did these simulations we did the MEA simulations, and the results are presented here. These are more of the technical results, and you see, as can be expected, that the steam consumption is nearly linear to the amount of CO2 captured, as is the compressor power. This is a CO2 compression unit, the CO2 compression power. The fan power prior to the CO2 capture unit, it is not linear. This is nowhere near linear. And the reason for that is that the power here depends on the flue gas flow rate and not on the CO2 captured. Because as you can see, the 2 points marked here, case 0401, which has a very low CO2 concentration. Thus, to capture the similar amount of CO2, you need a much higher, it has a much higher flue gas flow rate, and so the fan power is much larger than, say, case 0404, which has the highest CO2 concentration and thus a very low flue gas flow rate. And similarly, the pump power is also not very linear to the CO2 captured. So once we had the simulations performed, we then went to do the economic analysis. And here We started off by selecting 4 cases, which were over a wide range of sizes of the absorber and regenerator, and we took these 4 cases for detailed assessment. So what do I mean by detailed assessment here? Is that we developed very detailed equipment list for these 4 cases. And you can find these equipment lists as part of the report that is published by ieaghg and also on our website. So once we had these 4 detailed equipment lists for these 4 cases, then we calculate the equipment cost and then the total direct cost and indirect cost, plant cost, and so on and so forth to calculate the KPIs, which is the CO2 avoided cost or the cost of CO2 retrofit in a refinery for these 4 cases. Now, for the other 12 cases, what we did was we took the equipment cost for these 4 cases and developed equipment cost functions so that the results presented in this study can also be extended to other cases. So these equipment costs functions were then used to calculate the equipment cost for the other 12 cases. And as I mentioned earlier, the main reason for doing this was to actually develop these cost functions, which are also published as part of the report, so that other refineries or policymakers or researchers can take these cost functions and calculate the cost of the equipment cost for their particular case. So we also developed 2 types of cost function. One was a more generic cost function where you need lesser amount of information, and another case where you would get a better cost if you have the more information you have, as can be expected. So once we had all these 12 cases, the KPIs of all the 16 cases, then we can do some evaluation. And this is what I'll show you in the next few slides. Oh, I'm sorry, before I go on to show you the results, we want to show you the plot plan of base case 4. And the reason to show you this is that we're talking about the retrofit of a refinery. And a refinery is usually, there is hardly any space to put in a CO2 capture plant. As you can see from this figure, the green on the left side, the green rectangle on the left side represents the power plant. So that is where the new power plant went. The orange rectangle represents the absorbers, and the gray ones the flue gas desulfurization unit. As you can see, these are placed over tankages. So these tankages have to be moved. And they are the yellow rectangles you can see at the top right of the plot plan. Also, we needed a new cooling tower, which was at the bottom, is the light bluish unit at the bottom right of the power plant. There are new pipe racks that were installed, which are these hollow red rectangles, which are the new pipe racks, and then the CO2 pipeline, which is the green one, with the CO2 regeneration unit at the top of the plot plan, the sort of orange pinkish rectangles at the top there. So you see that when we talk about retrofitting, putting in a CO2 capture, retrofitting in a refinery, there is not only the cost of the capture plant, but also the cost of modifications that need to be made to the refinery. And these are important to consider in the overall cost, as we will see later. So here is the results for base case 4. So as you can see, the cost of retrofitting is much higher than what you would normally see in other reports. So the cost breakdown is approximately 30 to 40% of the costs are related to CO2 capture and conditioning. 45 to 55% are linked to utilities production, and this includes the natural gas, the the combined heat and power plant, the new cooling tower, and things of that sort, and 10 to 20% are linked to the interconnecting costs. So these are the modifications that need to be made in a refinery. So as you can see that this is a very important part of the cost. It's not small at all. The figure on the right shows it shows a similar curve, but here it shows the cost of CO2 capture as a function of the percentage of refinery emissions avoided. So here you can see that there is an economy of scale effect. The larger the capture unit, the lower the CO2 capture cost. However, you can also notice the effect of the flue gas desulfurization. So if you look at case 0405, which is the brown dot here, and case 0403, which is the red dot here, you could see that the case 0403, you don't see any economy of scale effect going from 0405 to 0403, and the reason for that is that we add a FCC unit, but we also add a flue gas desulfurization unit here. So you could see what the effect of the desulfurization unit is specifically in this case. Also, you can look at the effect of CO2 concentration, as in case 0404, which is the orange dot. So it has a low cost of CO2 capture, and that is because it has the highest CO2 concentration. So the cost of capture, even though it is a very small unit, the cost of it is very similar to that of the much larger units that you can see, 0405 and 0403. Yeah. So the reason, one of the other reasons is there are there's no FGD unit required in the SMR case, which is 0404. So moving on to the next slide, this shows the results for all the 16 cases that we considered. So here you could see overall the capture cost is very high, but that is due to the boundary conditions and assumptions that were made, such as no synergy with the existing plant, using MEA as the solvent, a very simple configuration. So what the results that are presented here in some sense present the upper bound or the upper extreme of the cost that you would see for retrofitting in a CO2 capture in a refinery. You can, as we talked about before, you can reduce the cost by considering a more advanced solvent and so on and so forth, or having a more advanced configuration, or doing heat integration with the existing refinery. Things of that sort, the cost would significantly come down. So the results presented here, I would want to emphasize, are more of an upper bound of the total cost. So I think we went through this during the presentation, but the main factors that affect the CO2 avoidance cost are the utility plant, specifically the natural gas cost, the CO2 concentration, the quantity of the CO2 captured, so the economy of scale, and the presence of flue gas desulfurization units. And also an important cost contributor is the interconnecting sections, that is the modifications you need to make in the plant. So in summary, ReCap has evaluated the cost of retrofitting CO2 captures and technologies in an integrated oil refinery and understands its implication to CO2 avoidance cost, the refinery fuel balance, the utilities requirement, and the constructability. I didn't talk much about constructability in this presentation, but we have a separate report on constructability analysis of CO2 captured in a refinery. Again, the costs are high here due to the level of detail and choices made, in particular putting in a new CHP plant. Also, we have provided the industry with data to estimate the impact of CO2 capture in their respective refineries. As I talked about earlier, we've allowed them, we've published cost laws to calculate the cost of individual sections of a CO2 capture plant, the absorption, regeneration, compression, and purification sections. We've developed a user-friendly Excel tool to calculate the CO2 avoidance cost and sensitivity of important parameters on the CO2 avoidance cost. My colleague Simon will go through this shortly once I'm done talking to you guys. And also we have presented a simple table with a range of CO2 avoidance costs and their underlying characteristics. And this is the table I talked about. So here we look at the CO2 avoidance cost in 4 different ranges, where the highest cost, which is at 210, is a very low concentration of flue gas coupled to a small amount of CO2 captured. So this is typically base case or ReCap case 0401. So you get a CO2 avoidance cost in range of $180 to $200 per ton of CO2 avoided. If you have low to medium CO2 concentration, which is 6 to 9%, a very low amount of CO2 captured, and a large fraction of the flue gases require desulfurization. The next range, $170 to $180 per ton of CO2 captured, is arrived at if you have low to medium CO2 concentration again, have a slightly higher amount of flue gas captured compared to the other case, and a smaller fraction of the flue gases require flue gas desulfurization. And finally, you get CO2 avoided cost in the range $160 to $170 per ton of CO2 avoided. And if you have medium to high CO2 concentration, the flue gas, a large amount of CO2 captured, and a very small fraction of the flue gases require flue gas desulfurization. So finally, what did we learn? How you provide steam matters, and I talked about this earlier. Having a additional CHP plant really increases the cost significantly. So if we can do some heat integration or provide a cheaper source of steam, you will reduce the cost. CO2 concentration matters. SOx matters, because then we would need to have a flue gas desulfurization unit. One important point here is SOx matters more in this case because we've considered MEA. So if you consider another solvent which doesn't degenerate so much in the presence of SOx, then it could be okay to do away with the flue gas desulfurization unit. So that could be an additional saving. Economy of scale matters, and I say weakly because it comes second to, so we saw earlier in the case 0405 and 0403, the economy of scale was overshadowed by the flue gas desulfurization unit. So in that sense, the other factors are more important than the economy of scale. Interconnection matters, so it's important to consider modifications in the refinery, where they constitute to 5 to 10% of the overall cost. And finally, refinery complexity does not matter. We looked at 4 different types of refineries when we started the project, thinking that the refinery complexity would be an important factor that affects the capture or CO2 avoidance cost. But we see that it doesn't matter to any extent as far as we could see. It could be due to the assumptions we made, but in general, we do not think that it matters as such. So that is my presentation so far, and I will now hand it over to my colleague Simon, who will present the Excel tool to you.
Hi, so I'm Simon Osanli, as Rahul said, and I worked more on the cost part of the project. And I'm gonna present you. Yeah, that's clear. And I'm gonna present you the Excel model that we have done and that can be used by you and industry. So this model can be defined on the project webpage. So it's at www.sintef.no/recap. And if you look on the web page, so you will find the report and the results that Rahul was presenting. And then at the bottom of the page, you have on the cost estimation part, you have spreadsheet for cost evaluation of CO2 capture from retrofit, which is the Excel model in a blank form that you can use to do your own estimate. And you also find here and this link for the 16 CO2 capture retrofit case, cost evaluation cases. Actually, all the cases that we have done as part of the ReCap project. So you can choose to either use a blank one or restart from an existing one if you have a case which is similar to yours in the case that we assessed. And I'm gonna present you the model over the case 4.3, which, as Rahul have explained, is the most complex case of considering the project. Yeah. So for simplicity and being user-friendly, the model had been made in Excel, and it's mainly decomposed in 6 pages. So the first one is presenting the model, so explaining what are in the different pages, providing instruction and recommendations on how to use the model. So starting a bit with the instructions, so it's telling you a bit on each page what you need to fill in, and I'll go through that a bit more in detail. But it's when you do a case, you start by providing project valuation data, so discount rate, reference years, number of years that should be considered for evaluation and utilization rate. Then you start to provide actually the CO2 stream data, both in terms of CO2 captured and also CO2 avoided through the CO2 emission leaked to the power plant. And then you pass through the evaluation of CapEx, and I'll get back to that a bit later, and also through the OpEx, both fixed and variable OpEx. And finally, you're providing choice regarding how to use excess power if your power plant is generating more power than required, and you can provide ranges on the sensitivity analysis to be considered. So once you'll have set all that, basically you'll have your result generated for the case that you want to consider. Before we get into how to fill in this number and how to get more suggestion, there's a few warning and a few things that are also made clear on the page. So some recommendation that you have to always be careful is always be careful about units when you put in your data, that it is about currency, also even about flows and stream. Always check that you're putting the numbers in the correct unit, otherwise you're gonna end up with wrong results. Of course, as said, you're free to use your own estimates, but if it is too challenging for you, you can of course use the equations and the cost function that have been developed as part of the ReCap project and that are available in the report, so you have where to find it. So that is true for the CapEx, but also regarding the utilities consumption and elements like that. This is also in the report, as Rahul was explaining the trend that you have and how you could use that to evaluate your own case. Yeah. Yeah, and I'll go through the data that you have. One thing which is important to say, and I'm guessing for most of the cases that will not be a problem, but the model that we have developed rely on the fact that you're looking at a case where CO2 implementation actually doesn't impact the production of the refinery. It's an assumption which is reasonable when you do retrofit and post-combustion, but if you look, for example, at some pre-combustion case or cases where you'll have modification of the refinery in terms of that are impacting the production, you should be careful, and you cannot actually use that model. It's a bit more tricky, and then you have to pass through something which is more similar to the levelized cost of electricity, like using in power generation. But here, to do the evaluation, you can use the CO2 avoided cost as passing through annualized CO2 capture capex and annual OPEX divided by the annual amount of CO2 avoided. And finally, about formatting, so you'll notice that most of the cells are locked except cell in orange, which are actually where you expect it to provide your input for evaluating your case. And finally, you have some information regarding contacts if you have questions for the spreadsheet, and also acknowledgement and disclaimer for the model. So now when you want to start doing your case, the first page where you're going to go is actually to go in this input page. So you're going to start by filling, as I was saying, project valuation data, so discount rate, reference year for cost, and here, for example, we put year 4 because the 3 first years we consider that you'll have the construction of the plant. You put the number of years of operation after the startup. You put the utilization rate. Then you get into the CO2 capture and avoided stream. So to get that, you provide the amount of CO2 that is captured per hour, and you also provide the amount of CO2 emitted by the power plant. And you get that from your case, and also from, you can generate the part on CO2 emitted from the power plant from the report as Rahul was presenting, if you do not have your own estimate. Once you have that, then you're going to put the cost by section for the capex part. So you're going to, for each of the sections that are considered, you're going to fill in direct material costs, construction costs, other operating costs, EPC costs. And we have divided the infrastructures into 3 main parts. So the CO2 capture and compression, the utilities, and the interconnecting. And in the CO2 capture and compression part, so you have the flue gas distillation unit, the absorber section, the regeneration, and the CO2 compression. In the utilities, you have the power plant, you have the cooling towers, and also you have the waste water treatment. And basically, for the case that you're going to do, you're going to fill in the cost that you want to put there. You can do that, as I was saying, based on your own estimates, but also based on the cost function that you have in the report. One thing which is important, if you're doing a case where you're going to have, for example, 2 or 3 absorber sections, you need to evaluate each of the absorber section individually, and then put the number together in the file. So once you have that, you can set in the parameters that are going to help getting to the total capital requirement based on the capex. So that is the contingency that are to be considered. So here we have considered 15% contingency of the total investment costs. You can fill in correction based on the spare parts cost contribution, on the startup cost, so for example related to maintenance, fuel costs and modification, and other costs. The numbers that are used here are standard ieaghg numbers, and this is something that you can also modify if you want to correct a case to be more to the value that you, for example, use it in your own company. And then you're filling in the allocation of cost over construction, so that you can report the cost properly when you're doing the evaluation of the CO2 avoidance cost. So once you have said that, your capex are estimated, and now you can pass through the OPEX, starting by the fixed operating cost. So to evaluate the labor, you'll be asked to fill in total number of employees, for the different part of the process, so capture, utilities, and interconnecting. And that is the number of employees total for the infrastructure. That's not the number of employees per shift. So just be careful about that. So it should be over the sum, the total number of employees you have related to that unit. You can put in the salary and the fully burdened salary, mean with social salaries and things like that. And then you'll have your labor cost estimated, and then you can get into the part about annual maintenance. So you can put factors, percentage, considering annual maintenance of the different units in the process. So that will give you your material maintenance, and then you can put an overhead on top of that to get the overall annual maintenance. Yeah. And finally, you can add a percentage for other costs, other fixed costs. Okay. So once you have done that, you can pass to the annual variable OPEX. And in there, you're going to first start to fill in your utilities consumption that you can, for example, estimate based on the report if you don't have made your own simulations. And you can, for example, fill in the natural gas consumption for the power plant, the amount of calcium carbonate, the pure MEA solvent that you need for the makeup, raw material for the system, and also the amount of MEA sludge to be disposed for. One thing which is also fitting in this part is actually the share of the natural gas consumption, which is linked to produce steam for the CO2 stripping, because the CHP plant is producing both electricity and steam. And actually, what we are putting here as a number is a number which actually will tell you how much of the cost of the power plant are related to the steam part and the electricity part, which then give a good basis for the sensitivity analysis to see, for example, what is the impact of steam consumption in the system. So the number which is here is a good first, I think, first approximate, and you can refine that depending on your case that you have. Once you have your utilities set in, you can then set in your annual the molecular sieve replacement for the drying before conditioning or during conditioning. And finally, you then need to set the cost of utilities and materials. So for example, natural gas price, MEA price, and stuff like that. As I was saying, one important element also is that sometimes you have designed the plant and to meet the steam requirement, and actually you may result at the point where you produce a bit of excess power, and here you have a small part which is actually allowing you to consider that you actually value this excess power by, for example, being able to valorize it internally or reselling it at a given price. So you can choose to take that into account or not. Regarding, as I was saying, the model is also directly evaluating sensitivity analysis for the cases, and you can actually set in the ranges that you want to provide. So both for the different part of the process in percentage in variation range, but also for project valuation data in absolute numbers. So for example, you can set that the project duration considered for sensitivity analysis will be between 10 and 40 years. Okay. So actually, once you have filled that up, then you're all set to go, and we can go through the different pages that are used. So I can just explain you before we get to the result what is this page called discount factors. It's actually using the data for the project valuation, so that to calculate the discount factor actually, which is used to pass from capex or total capital cost requirement to actually the annualized value. So based on the discount rate and the project duration, basically it's going to give a number by which the capex have to be divided to have a constant annualized cost over the project duration repaid over the operation of the project. So, and this is for the base case, and you have this number for actually the sensitivity analysis. Yeah. It's also depend on the utilization rate. I forgot to say that. Okay, but yeah, to get to the results. So once you have set in all your results, actually you can go to the detailed cost result page, and there actually you'll have the breakdown from for the CO2 capture retrofit. So you'll have the overall cost in $1,000, and you'll have the breakdown by section until the total install cost and the process contingency, and then you'll have the total plant cost and the total requirement, capital requirement given for each of the section of the plant, and of course for the total part of the plant. So similarly, as I was saying, then for the OPEX, you'll have the cost provided in $1,000 per year for the different section, and you'll have the breakdown between labor costs, annual maintenance, but also the overall number for annual fixed costs, and also for the different part regarding natural gas consumption, chemical and catalyst costs, and things like that. And if you have setting that you wanted to valorize electricity or excess electricity, you'll also have numbers for that. So based on this, actually, then you'll have an annualized capex calculated and an annualized operating cost, which give you a total annualized cost. And then this number is divided by the total amount, the annual amount of CO2 captured and avoided to get the cost of retrofitting CO2 capture. And this is more detailed result, and if you want to have a simple summary, you can find that on the page called Summarize Cost Results, and you'll actually have the overall number given here at the bottom, and you'll have cost in dollar per ton of CO2 avoided with breakdown between sections, so for the different part of the plant, and also with breakdown between capex, fixed opex, and variable opex. And you'll have a few charts generated giving you a quick idea of what are the proportion between the different elements, both at the comparison between part of the plant, so CO2 capture and compression, utilities and interconnecting, but also in terms of a more detailed breakdown. And finally, one thing which is also very interesting is to look at the sensitivity analysis to both see how uncertainties that you may have in your assessment can impact your cost, but also how potential improvement actually could help reducing the cost. So you'll find here in the page called sensitivity analysis for the different parameters that are considered, actually the impact of the variation, both for the low value of the variation and the high value, and both in dollar per ton of CO2 avoided, you'll find the variation in percentage, and you'll find actually the chart presenting the results. One thing that can happen is that depending on the range that you have selected and the value that you have, the numbers that are the bars that are displayed here may be outside of the chart. So just be careful to you can just recheck the bar and just need to make sure that it's in the proper range if you do not see these color bars. So I think that's it for me, and if you have a question, you can shoot us an email and we'll see if we can help you with that. We advise you to have a look at both the Excel file and once again at the report, which provide quite a lot of information to help you doing evaluation. Okay, then thank you for your attention. And I guess we're going to pass to a question part.
Yes. Now. Thank you, Rahul and Simon, for presenting the webinar today. So as Simon's just said, if you want to email, so if you have further questions to this presentation, if you want to email me, suzanne.gillick@ieaghg.org, I can easily pass those questions on to Simon and Rahul. Otherwise, we look forward to you joining us again at future webinars, and thank you and goodbye.